Alrighty. So in this video, we're going to be talking about integration by parts, which is our first BC lesson. How fun. Back in AB, we talked a lot about integration techniques, let's say manipulating the integrand or using U sub, or maybe even doing long division or synthetic division to divide that out to make it easier. Integration by parts is another integration techniques that we'll be using, and this is basically the product rule for integration. So you can see here, the little rule is the integral of u dv is equal to uv minus the integral of v du. U is going to be a function and dv is going to be another function. We're going to figure out how to get those functions and then integrate them. We're going to have some tips and tricks on how to figure out what u is and what dv is in terms of my two functions that I have in my integrand. So we're going to choose dv so that it can be integrated easily to get v. We don't want any nasty integrations, okay? We're also going to be choosing u so that we can take the derivative easily, obviously. It helps if du is simpler than u and v is simpler than dv. We're also going to be choosing u in this order. This one's going to be the most important tip. We're going to go from inverse, trig, then we're going to go to logs, then your polynomials, then your trig, then your exponential. In this case, we have a little mnemonic, I late, or I love latte, I late. Another thing that we're also going to be using is this little pattern right here that helps us keep everything in order and shape. As a disclaimer, my u's and my dv's are not going to be pretty because I write my v's like u's and u's like v's, so it's not going to be pretty. And if you're the type of person that does that, maybe choose another letter just to help you a little bit. But let's go ahead and do number one. We want to integrate x cosine of x dx, and obviously I can't use u substitution or I can't use any other integration techniques. So I'm going to use integration by parts and I'm going to choose u first. U is always going to be my main goal. In this case, if I were to look at I latte and look at the order, you'll notice that algebraic, my x, comes first, then my little trig function. So x is going to be my u, which means that dv is going to be my cosine of x dx. So this whole thing right here. All right, now I'm going to find out what du is by taking the derivative of x, which is just 1. And then to find v, I'm going to take the integral of cosine of x, which is just sine of x. Once you have everything neat in place, we're going to go ahead and use my little formula. So uv minus the integral of v du, and plug in everything I know. So use x, v sine of x, minus the integral of v, which is sine of x, and then du, which is just 1 dx. All right, I'm going to integrate sine of x dx, which is just negative cosine. Of course, don't forget about your plus c. Simplify this a little bit, and you get x sine of x plus cosine of x plus c. Now, let's say that you want to be goofy, and let's say that you wanted to use cosine of x to be u. And let's see why that is not not pretty. Oops. If u is cosine of x, that means that dv is going to be x, okay? And this is just for show and tell, not the real thing. This means that du is going to be negative sine of x dx, and then v is 1/2 x squared. I could already see it now because my integral of x is 1/2 x squared. That's not pretty, okay? That's nasty. I have uv minus the integral of v du. See, this is a v. I promise you that's a v, and this is a v, okay? See how my v's and u's are, they look the same. I'm sorry. So we have cosine of x times 1/2 x squared minus the integral of 1/2 x squared, and then my du is negative sine of x dx. Notice how here, this is another integration by parts problem, because I can't take the integral of that. I can't use u sub of that. Because you can't do that, that's going to be a little indication of saying u is not cosine, but u is x. That's why we have this little order in place where we have inverse trig, log, then your algebraic, then your trig, then your exponential. So your final answer here was the thing that we did 2 seconds ago, right here. All right, number 2, we are still using this pattern right here. I'm going to cheat a little bit and copy it so that my u's and v's are pretty. All right, so I have the integral of ln of x dx. We're going to put times 1 right here just so that you know that it is being multiplied by something, aka 1. And if I were to look at my order, my hierarchy, notice how logs is first, then your algebraic. Since logs is first, I'm going to have u to be 1. Oops, not 1, ln of x. And then I'm going to have dv to be 1 dx, my leftover. du is going to be 1 over x dx, and then the integral of 1 is just x, which is pretty. Okay, so then I'm going to have uv minus the integral of v du. uv is just us multiplying across. That's x ln of x minus the integral of v, which is x, and then du, which is 1 over x dx. Simplify that integral a little bit. The x's will cancel out, so you're just left with the integral of 1, which is just plot twist x. And then, of course, don't forget about your plus c. Number 3, same thing. So let me go ahead and copy this. We have x squared, and then we have e to the x. Anytime you see an exponential, go ahead and put that in dv. Okay, that's going to be the last thing that you want as u, just because the integral of e to the x is going to be e to the x, or the derivative of e to the x is e to the x. And it's just easier for you to put dv as the exponential, because here x squared, we could easily take the derivative of that. That's 2x. That's great. So now I have uv minus integral of v du, multiply across, so that's x squared e to the x, minus the integral of e to the x, and then 2x dx. So I'm going to give that a little bit. Now, you might be thinking, oh no, this is integration by parts again, because I can't take the integral of this. Unfortunately, you do have to use integration by parts twice for this problem. Either way, if you were to make u to be e to the x and dv to be x squared, you're going to make it harder on yourself, because then v is going to be 1/3 x to the 3rd power. And that's just nasty. You don't want to do that. Okay, so I'm going to use integration by parts again. I'm going to figure out what u, dv, du, and v is. Once again, we're still using the same steps where we're using I late. In this case, since I have my algebraic first, that's going to be my u. My dv is going to be e to the x dx. V is still going to be e to the x because the integral of e to the x is e to the x. And then my du is 2 dx. All right, once I do uv minus the integral of v du, I'm going to get 2x e to the x. Remember, that's just me multiplying across. Minus the integral of v du, so which is e to x times 2 dx. And yay, we can integrate that easily, because that is just 2e to the x. And then, of course, here plus c. Now, remember that this final thing in green is this thing in blue that we just evaluated. Don't forget that we still have this right here and this negative sign right here. So your final answer should look something like this. And of course, make it pretty by simplifying the negative and distributing it. So you get this lovely thing as your answer. I know, that's crazy. All right, so those first three examples, we didn't have to use any bounds of integration. For number 4, we have a definite integral where we are evaluating from 0 to 1, inverse tangent of x dx. Anytime you see inverse trig, that's I, your I latte, I late. I is inverse trig. So your u is going to be inverse tangent. And then your du is going to be the derivative of that. And hopefully from your AB class, you remember that. Your dv is going to be 1 dx, which means that v is x, which is pretty. That's great. All right, so you have uv minus the integral v du, uv multiply across, x inverse tangent of x, minus the integral of v, and then du. So x 1 plus x squared. Now, because this is a definite integral, you still want to have bounds here on the left side, even though it's not explicitly stated. Remember that your bounds are still from 0 to 1. I'm going to integrate this first, not integrate, I'm going to evaluate this first just because it's easiest for me to evaluate this. I'm going to plug in 1 and 0. Oops. Well, don't plug in 0 just because 0 times that thing right here is just going to be 0 anyways. So now you have 1 times inverse tangent of 1. When's that? Well, hopefully you know your unit circle. That's just pi over 4. So that's this part right here. I still have to deal with this integral right here. And this integral, I forgot the dx, is u sub. So I have u to be 1 plus x squared. I have du to be 2x dx. And if I were to use u sub, I get 1/2 the integral of 1 over u du. Now, because I'm changing my bounds of integration and using u sub, I need to change my bounds. So they can't be from 0 to 1 anymore. It has to be from 1 to 2. Me evaluating 0 and 1 into this expression right here. I'm going to integrate, so that's going to give me 1/2 ln of u from 1 to 2, 1/2 ln of 2 minus ln of 1, and remember that ln of 1 is 0, so technically you're just left with 1/2 ln of 2. That's this answer right here. You're going to put everything together, so now you have pi over 4, which is the left side, minus 1/2 ln of 2. And that's your final answer. All right, so I'm going to give you another method of integration by parts, and this is an easier method, and it's called the tabular integration. What that is basically if you have f of x and g of x, and one of them you can take the derivative until you get a 0, and then one of them you can integrate and know the integrals for that, then you could use the tabular integration method. You're going to pick what u is, aka the derivative, and see when it goes to 0. So you're going to make a list of derivatives and integrals side by side. You're going to link the parts diagonally, and then you're going to alternate signs, and we'll talk about what that means, and then we'll combine. So remember how we did this example right here, number 3, and we had to use integration by parts 2 times? Well, I'm going to use the tabular method with this right here. Notice how I could take the derivative of x squared to get 2x, and then to get 2, and then take it 0. Since I could take the derivative all the way to 0, I could do that. And then my dv, lucky for us, the derivative, not the derivative, the integral of e to the x is just e to the x. We're going to link diagonally, and we're going to multiply them. And then what I mean by alternating signs is that this is going to be positive, this is going to be negative, and then this is going to be positive whenever we multiply them. So here, I'm going to multiply x squared and e to the x. Here, I'm going to multiply 2x and e to the x, but since I have a negative, it's going to be negative. And then here, I have 2 and e to the x, so plus 2 e to the x, and then I have plus c. Notice how that is the same thing as, oh, guess what? This right here. Isn't that crazy? And I only did this in like 2 seconds. Of course, this only works whenever you can take the derivative to 0 and you can integrate easily. In these examples right here, I don't tell you if you could use the tabular integration method or not. You're just going to have to figure that out by yourself. So, like number 6 right here, I can integrate x squared, but the integral of ln x, I can't do that. So for number 6, you're probably going to have to stick with the traditional integration by parts and do that way. Now, number 7, though, we could do that because the integral of sine of x is just going to be cosine, and then it's just going to be alternating with sines and cosines. So here for number 7, I'm going to have u to be x, then 1, then 0. So I could take the the derivative easily there. And then my integral of sine x. The integral of sine of x is going to be negative cosine of x. And then the integral of negative cosine of x is negative sine of x. I am going to link my diagonals. And then I'm going to alternate signs. And then I'm going to combine. So that's going to be negative x cosine of x plus sine of x. Now, this is a definite integral from pi over 2 to pi. So we're still evaluating. We have negative pi cosine of pi plus sine of pi minus negative pi over 2 cosine pi over 2 plus sine pi over 2. If you want to leave it like that, you can. However, it's pi and pi over 2. It's easy because it's on the unit circle, okay? So we know that cosine of pi is negative 1. Sine of pi is 0. We have cosine of pi over 2, which is 0. And then sine pi over 2 is 1. So your final answer is just pi minus 1. Crazy. All right. So the last thing that I want to do is this FRQ back in 2008. What I want you guys to do first is obviously pause the video, take 15 minutes of your time, and then do the FRQ on your own before you watch the video, and then, you can play it. All right, so we have the derivative of a function f is given by this lovely thing for x is greater than 0 and f of 1 is equal to 7. Part A says the function f has a critical point at 3, which we could see here, that's true. And at this point, we want to see if it is a relative min, a relative max, or neither, and we want to justify our answer. So the only critical point for f prime of x is just 3, just because e to the x can't be 0. So I'm going to do a little sign chart at 3. I'm going to pick 0, and I'm going to pick 4. So at 0 here, this is going to be negative, and this is going to be positive. So negative, positive makes a negative. At 4, this is going to be positive, and this is going to be positive. So this is positive, which means that I am going to have a relative minimum since I go from negative to positive. Now, remember that a sign chart is not a valid justification. What you're going to have to do is write out your little sentence by saying, oops, that's too big. By saying f has a relative minimum at x is equal to 3 because f prime changes signs from negative to positive at x is equal to 3. There's your little justification. Okay, part B. On what intervals, if any, is the graph of f both decreasing and concave up? Explain your reasoning. Now, because we have a concave up function, what we're going to do is take the derivative again to get the second derivative. So I'm going to copy down this. I'm going to take the second derivative. So that's first times the derivative of the second plus second times the derivative of the first. Clean this up a little bit. So you have e to the x times x minus 2, which means that your only critical point is at 2. I'm going to plug in 1, and I'm going to plug in 3. So if I were to plug in 1, that's positive, this is negative, so this is negative. And then if I were to plug in 3, this is positive, positive, so this is positive. And remember that concave up means that your second derivative is positive, which is in this region right here. We also know that f is decreasing when our derivative is negative, which is in this region right here. So your little justification needs to have both decreasing and concave up. So f is decreasing on 0 to 3, and this is from work in part A, because the derivative, or because f prime, is negative on this interval. F is concave up on 2 to infinity because f double prime is positive on this interval. Therefore, f is both decreasing and concave up on the interval blank. And of course, we're just going to find out where they are common. Since this is from 0 to 3 and this is from 2 to infinity, this means that it's both decreasing and concave up on the interval 2, 3. Okay, now we want to find the value of f of 3, which is where our integration by parts comes in. So we have 1 to 3, f prime of x is equal to f of 3 minus f of 1. And we want to find f of 3, so we have f of 1 plus 1 to 3, f prime of x is equal to f of 3. All right. From the sum, the question sum, I already know that f of 1 is 7, and I already know that this is my little derivative right there. So I have 7 plus 1 to 3 dx. All right. So to evaluate this, we're going to have to use integration by parts. I'm going to use the tabular method just because you have e to the x, and that's going to be your dv, because guess what? The integral of e to the x, yeah, it's just e to the x, which means that u is going to be x minus 3 because I could take the derivative of that, that becomes 1. Take the derivative of that again, that becomes 0. Alternate your signs, which is going to give us e to the x minus 3, minus e to the x. Now, this is the part where your algebra skills needs to come in. Okay, factor this. Make it pretty. Notice how I factored out e to the x, and that gave me e to the x times x minus 4, and my bounds are from 1 to 3. So now I have e to the third power 3 minus 4, which is negative 1, minus e to the first power 1 minus 4 is negative 3, and that is my answer for my integral. Of course, we still have the 7 laying around on the my first term, so don't forget about your 7 here. And then, of course, just make it pretty, okay? So 7 minus e to the third power plus 3e to the first power. If you don't want to make it pretty, that's fine. Just so that you don't risk losing your answer point if you mistakenly simplify incorrectly. All right, there are other problems that we haven't done, such as 10, 11, 8, 9, 5, and 6. So go ahead and do those for extra practice. And then we'll talk about partial fractions and improper integrals on the next video.